When you let go of an object, it falls. That simple drop, repeated 1,000 times in a childhood, becomes so familiar that it feels like a property of the object itself, as if matter carries a built-in instruction to move downward. But if you step back and look carefully, gravity is stranger than that. It does not behave like a push or a pull in the usual sense. It does not weaken because you stop believing in it, and it does not vanish when the space between objects seems empty. It acts through what looks like nothing at all, and it shapes motion with a precision that can be measured with clocks, with telescopes, and with instruments sensitive enough to notice the smallest change in time. For a long time, the best description was Newton's. Every mass attracts every other mass. The strength of the attraction depends on how much mass there is and how far apart the objects are. With that single idea, you can explain the fall of an apple and the orbit of the moon. You can predict the motions of planets, the return of comets, and the timing of eclipses. Even now, in most everyday conditions, Newton's description works so well that it feels final. But Newton's gravity carries an uncomfortable silence. It tells you what the force does, but not what the force is. It gives you a rule, not a mechanism. Two bodies separated by a vast emptiness still influence each other, and the theory does not explain how the influence travels. The shift begins when you notice something that sounds ordinary but is deeply revealing. If you are inside a closed elevator and the cables snap, you and everything around you fall together. In that moment, objects no longer press against your hand. A coin released from your fingers does not drop away from you. It floats beside you. You feel weightless, even though gravity is still present. Nothing about the Earth changed. Nothing about the mass below you changed. What changed was your state of motion. You and the coin share the same free fall. This is not a trick of perception. It points to a physical principle. In a small enough region of space and time, free fall erases the local effects of gravity. Einstein recognized that this is not what a typical force does. If you place a charged particle in an electric field, you cannot make that field disappear by simply falling. The field still accelerates the particle relative to nearby neutral objects. Gravity is different. In free fall, all objects share the same acceleration, regardless of their internal composition. That universality is the clue. From that clue comes a new picture. Gravity is not treated as a force acting inside space. It is treated as a feature of space and time themselves. Space and time are not separate backgrounds. They form a single structure, space-time. And space-time is not rigid. It can curve, it can stretch, it can respond to the presence of energy and momentum. Matter and energy shape the geometry. The geometry shapes motion. In this view, a falling object is not being pulled by an invisible hand. It is moving along the straightest possible path available in a curved geometry. That path is called a geodesic. In ordinary flat space, the straightest path looks like a straight line. In curved space-time, the straightest path can look curved when you draw it on a map. The object is not choosing to curve. It is moving freely, and the geometry is doing the bending. This is why orbiting is a kind of falling. A satellite around Earth is in continuous free fall, always dropping toward Earth, but moving forward fast enough that the ground curves away beneath it. From the satellite's perspective, it is weightless because it is following a geodesic. The sensation of weight that you feel while standing still is not gravity pulling you down. It is the ground pushing you up, preventing you from following the geodesic that your body would otherwise take. Einstein's field equations make this relationship quantitative. They connect the distribution of energy, momentum, and pressure to the curvature of spacetime. The equations do not describe gravity as a substance flowing through space. They describe a constraint. Given a certain content of energy and momentum, spacetime must curve in a specific way. Given that curvature, the trajectories of objects and light are determined. The power of this description is that it makes predictions that can be tested. One famous test involves Mercury. Mercury's orbit does not trace the same ellipse forever. The point of closest approach shifts over time. Newtonian gravity predicts most of that shift because other planets perturb Mercury's motion, but not all of it. The remaining part is explained by general relativity. The geometry near the Sun is slightly curved, and Mercury's path responds to that curvature. The measured value matches the relativistic prediction. Time also becomes an observable signal of curvature. In stronger gravity, time runs more slowly. A clock closer to a massive body ticks at a different rate than a clock farther away. This has been measured with high precision. It is also essential for technology. Satellites used for navigation carry clocks that must be corrected because their motion and their position in Earth's gravitational field change the rate at which time passes for them. If those relativistic corrections are ignored, the computed positions drift by large distances in a single day. The geometry of spacetime becomes part of everyday engineering. Light, too, follows the geometry. In this theory, light does not slow down in the usual sense, but the path it takes through spacetime can allow it to arrive later than you would expect from a flat geometry, and it can bend around massive objects. Starlight passing near the Sun is deflected by a small, measurable amount. On much larger scales, galaxies and clusters of galaxies bend light from more distant sources, producing arcs and multiple images. This gravitational lensing is, now, a routine observational tool used to map mass in the universe, including mass that emits no light. General relativity also predicts that changing mass distributions can produce ripples in spacetime itself. These are gravitational waves. They are not waves traveling through spacetime like sound through air. They are oscillations of spacetime geometry. When compact objects like black holes or neutron stars orbit and merge, they radiate energy away as gravitational waves. Instruments on Earth have measured these signals directly. The waveforms match the predictions of relativity to high accuracy, confirming that spacetime can carry energy and that gravity is not merely a static field, but a dynamic geometry. So the modern description of gravity, at least within the domain where it has been tested, is not a force in the Newtonian sense. It is geometry. It is the structure of spacetime, shaped by energy and momentum, guiding the motion of matter and light. This is not a metaphor. It is a framework that survives precise experiments, from planetary motion to clock comparisons to the detection of gravitational waves. And yet, even here, with all this success, a quiet tension remains. Geometry describes how gravity behaves, but it does not tell us what spacetime is made of, or whether it is made of anything at all. It treats spacetime as a smooth continuum, but other parts of physics describe nature in quantum terms, where discreteness and uncertainty are unavoidable. Gravity fits perfectly into one side of modern physics, and awkwardly into the other. The more precisely we confirm gravity as geometry, the more sharply we feel the edge of what we do not yet understand. The geometric description of gravity carries an implication that is easy to miss at first. If gravity is geometry, then it does not sit inside spacetime as one phenomenon among others. It defines the structure in which all other phenomena unfold. Fields propagate, particles move, clocks tick, and light travels within a geometry that is itself dynamical. This makes gravity different in kind, not just in strength. The other interactions act within spacetime. Gravity shapes spacetime. This difference becomes especially clear when gravity is compared to electromagnetism. An electric field exists at a point in space and time. You can place a charged particle there and measure the force it experiences. You can shield the field or cancel it with another field. Gravity does not behave this way. You cannot shield it. You cannot turn it off. And in free fall, you cannot even locally detect it. A freely falling laboratory is indistinguishable from an inertial one, at least over small regions. This property is not an accident. It is built into the geometric structure of the theory. Because gravity is geometry, it does not have a local energy density in the same sense as other fields. You can talk about the energy of an electromagnetic field at a point, but you cannot define the energy of the gravitational field at a point without ambiguity. This is not a flaw in the mathematics. It reflects the fact that gravity is tied to the coordinate system itself. Energy conservation still holds globally in appropriate settings, but locally, the concept becomes subtle. Geometry resists being treated like a conventional field. This subtlety appears again when gravity is pushed to extremes. Near very massive objects, space-time curvature becomes strong. Paths that once seemed straight converge. Time slows dramatically. In the most extreme cases predicted by general relativity, space-time develops regions from which no signals can escape. These regions are bounded by surfaces called event horizons. Outside the horizon, space-time behaves in familiar ways. Inside, the geometry tilts so strongly that all future-directed paths point inward. Black holes are not introduced here as exotic objects, but as natural solutions of the same geometric equations. They arise when enough mass is compressed into a small enough region. Nothing about them requires new assumptions beyond general relativity. Their existence is supported by observations of stellar motion, by high-energy radiation from accretion disks, and by gravitational wave signals from mergers. They represent gravity pushed to its logical limit within the geometric framework. Even so, general relativity treats spacetime as smooth at all scales. Curvature can become large, but the underlying structure remains continuous. This is where the theory begins to strain against the rest of physics. Quantum mechanics describes nature in terms of discrete interactions and probabilistic outcomes. Fields fluctuate. Energy comes in quanta. At very small scales, uncertainty is unavoidable. Yet space-time in general relativity has no built-in smallest unit. It can be subdivided endlessly in principle. Attempts to merge these two frameworks reveal the tension clearly. When gravity is treated as a quantum field in the same way as other forces, calculations produce infinities that cannot be removed by known techniques. These divergences are not merely technical inconveniences. They suggest that something about the geometric description breaks down at very small scales. Either space-time itself must change character, or gravity must be understood in a different way. What is important at this stage is restraint. None of these difficulties invalidate general relativity where it has been tested. On the contrary, they highlight its domain of success. The geometric description works extraordinarily well from everyday scales up through astrophysical and cosmological regimes. It explains the expansion of the universe, the bending of light, the behavior of compact objects, and the propagation of gravitational waves. Any deeper theory must reproduce these results as an approximation. This is why gravity is often described as a low-energy effective theory. It captures the large-scale behavior of spacetime without necessarily revealing its microscopic structure. Just as the equations of fluid dynamics describe the flow of water without referencing individual molecules, general relativity may describe the smooth behavior of spacetime without revealing its underlying degrees of freedom. This analogy is suggestive but limited. Water is made of molecules that can be directly observed and manipulated. Spacetime, if it has constituents, does not reveal them so easily. Still, the idea that geometry might emerge from something deeper is difficult to ignore. The equations of gravity resemble thermodynamic relations in certain limits. Horizons behave like systems with temperature. Black holes possess entropy proportional to surface area. These facts do not yet redefine gravity, but they hint that geometry and information may be connected in ways not fully understood. At this point, these hints remain within established physics. They do not require speculation about consciousness or metaphysics. They arise from careful analysis of known equations. For now, gravity stands as a description of how spacetime behaves under the influence of energy and momentum. It is geometric, not because geometry is fashionable, but because experiments demand it. Clocks run differently, light bends, waves propagate through emptiness. These are not interpretations layered on top of the data. They are the data. Understanding gravity as geometry does not solve the deepest questions. It sharpens them. If space-time curves, what does that curvature represent at a fundamental level? Is space-time a basic ingredient of reality, or is it an emergent structure arising from more primitive elements? General relativity remains silent on this point. It provides the rules, not the origin. The significance of this silence will become clearer when other physical quantities are introduced that share unexpected similarities with geometry. Among them is entropy, a concept that begins in thermodynamics and statistical mechanics, but appears again and again wherever horizons and limits arise. Before any connection between gravity and entropy can be explored, entropy itself must be understood precisely, without metaphor and without ambiguity. The geometric view of gravity also changes how emptiness itself is understood. In Newtonian physics, space is a container. It holds objects, but it does not participate in events. In general relativity, space and time are active. They respond. They evolve. They carry information about energy and momentum, and they influence how all physical processes unfold. What once appeared as an inert background becomes part of the dynamics. This shift has practical consequences. Consider how distances are measured. In flat geometry, the shortest path between 2 points is a straight line, and the rules of geometry are fixed. In curved spacetime, distances depend on the path taken and on the gravitational environment. Two observers following different trajectories can disagree on how much time has passed between the same pair of events. This is not a disagreement caused by faulty instruments. It is a property of the geometry itself. Time becomes a dimension that can stretch and compress. This is why gravity affects clocks. A clock near a massive object ticks more slowly than an identical clock far away. This difference accumulates steadily. It is not an illusion. It is not a signal delay. It is a real difference in elapsed time. Experiments using atomic clocks placed at different heights confirm this effect with extraordinary precision. Time itself is part of the geometry, and gravity reshapes it. Once this is accepted, the distinction between space and time loses its absolute meaning. Events that seem simultaneous to one observer may not be simultaneous to another. Paths that look straight in one coordinate system may look curved in another. The underlying reality is not a single preferred grid, but a flexible geometric structure that accommodates many descriptions. The laws of physics remain consistent across these descriptions, but the geometry adapts. General relativity expresses this adaptability through its mathematical form. The equations are written in a way that does not privilege any particular coordinate system. They describe relationships between geometric quantities and physical sources that hold regardless of how space-time is labeled. This is why gravity can be described equally well near Earth, near the Sun, or near a black hole, using the same underlying principles. The geometry changes, but the rules do not. This universality is one of the theory's greatest strengths. It allows gravity to be applied to systems ranging from laboratory experiments to the evolution of the entire universe. On cosmological scales, space-time curvature describes the expansion of the universe. Galaxies are not flying through space away from one another like debris from an explosion. The space between them is stretching. Distances grow because the geometry itself evolves over time. Observations of distant galaxies show that this expansion is ongoing. Light arriving from far away carries information about the geometry of space-time when it was emitted. By studying that light, physicists reconstruct how the universe has changed. General relativity provides the framework for this reconstruction. It connects the distribution of matter and energy to the large-scale shape and evolution of space-time. Despite this success, the theory remains incomplete in a specific and important sense. It does not explain why space-time exists or why it has the properties it does. It assumes a smooth continuum and treats it as fundamental. This assumption works remarkably well at accessible scales, but it may fail at extremely small distances, where quantum effects become significant. At those scales, the concept of a smooth geometry may lose meaning. The fact that gravity resists quantization is not ignored. It is studied carefully. Physicists have tried many approaches to reconcile gravity with quantum mechanics, but none has yet produced a complete and experimentally confirmed theory. What remains clear is that any successful theory must reproduce general relativity in the appropriate limit. The geometric description is not optional, it is enforced by observation. This places gravity in a unique position. It is both deeply understood and deeply mysterious. Its equations are known, its predictions are precise, its domain of validity is vast, and yet, its relationship to the rest of physics remains unresolved. This tension is not a flaw to be dismissed. It is a signal that something fundamental is missing. At this stage, however, the foundation is firm. Gravity, as far as current evidence shows, is a geometric phenomenon. It is not a force propagating through space. It is the structure of space-time itself, responding to energy and momentum. Any further discussion about gravity emerging from other concepts must respect this foundation. It cannot replace it. It must explain it. Only after this geometric picture is fully established does it make sense to introduce other quantities that may play a deeper role. One of these quantities appears in thermodynamics, in statistical mechanics, and in the behavior of systems with many degrees of freedom. It is measurable, it is calculable, and it places strict limits on what physical systems can do. That quantity is entropy. Before entropy is associated with gravity, information, or the structure of space-time, it must be understood in its original and most precise form. Entropy is not a metaphor, it is not a measure of disorder in a vague sense, and it is not a philosophical statement about chaos or decay. Entropy is a physical quantity with a strict mathematical definition, rooted in thermodynamics and statistical mechanics. Its meaning is subtle, but it is exact. The concept of entropy first emerged from attempts to understand heat. In the 19th century, engineers and physicists were trying to improve steam engines. They noticed that heat naturally flows from hot objects to cold ones, and never the reverse. You can place a cold object next to a warm one and watch the temperatures equalize. But you never observe heat spontaneously flowing from cold to hot without external intervention. This directionality was not explained by Newton's laws, which work just as well forward or backward in time. To describe this asymmetry, entropy was introduced. In classical thermodynamics, entropy is a quantity that increases in isolated systems. When a process occurs naturally, the total entropy of the system and its surroundings does not decrease. This is known as the second law of thermodynamics. It is one of the most reliable principles in physics. No experiment has ever contradicted it. At first, entropy was defined operationally. It was linked to heat transfer and temperature through precise relationships. But this definition did not explain why entropy behaves the way it does. It described the rule, not the reason. The deeper explanation came with the development of statistical mechanics. Statistical mechanics connects the behavior of large-scale systems to the microscopic states of their constituents. A system made of many particles can be arranged internally in many different ways, even if it looks the same from the outside. These internal arrangements are called microstates. The large-scale description, defined by quantities like pressure, volume, and temperature, is called the macrostate. Entropy measures how many microstates correspond to a given macrostate. This relationship was made precise by Ludwig Boltzmann. In this formulation, entropy is proportional to the logarithm of the number of microstates compatible with the observed macrostate. When a system evolves toward equilibrium, it moves toward macrostates that can be realized by more microstates. This is not because the system prefers disorder, but because there are overwhelmingly more ways to be in those states. Consider a box filled with gas. If all the gas molecules start in one corner, that is a possible configuration. but it corresponds to very few microstates. If the gas spreads evenly throughout the box, that macrostate can be realized in an enormous number of microscopic arrangements. The laws of motion allow both configurations, but the second one is vastly more likely. Entropy increases because probability favors states with more microstates. This statistical view explains why entropy increase appears irreversible. The underlying laws governing individual particles are time-symmetric. They do not distinguish past from future. But when many particles are involved, the probability of spontaneously moving from a high entropy macrostate to a low entropy one becomes astronomically small. It is not forbidden, but it is so unlikely that it never occurs in practice. Entropy also provides a natural direction for time. While the equations of motion do not define an arrow of time, entropy does. The direction in which entropy increases is the direction we call the future. This does not mean time is caused by entropy. It means that entropy growth gives time a physical orientation in macroscopic systems. Importantly, entropy is measurable. It can be calculated from thermodynamic data. It can be inferred from microscopic models. It is not subjective. It does not depend on human perception. It is a property of physical systems. At this point, entropy has been defined without reference to gravity, spacetime, or information theory. It is a quantity that emerges from counting possibilities. It governs heat engines, chemical reactions, and phase transitions. Its laws are as well tested as those of mechanics. Only later does entropy appear in contexts where gravity is present. When that happens, it does not change its meaning. The same quantity that governs steam engines also governs black holes and horizons. That fact is not assumed, it is discovered. Entropy becomes even clearer when its consequences are followed carefully through real physical processes. Take a simple example. A hot object placed in a cooler room slowly cools down. Energy spreads out. Temperature differences shrink. Nothing in the microscopic laws forces this to happen in one direction only, yet it always does. The reason is not hidden in the equations of motion. It lies in counting. When energy is concentrated in one place, there are relatively few microscopic arrangements that produce that concentration. When energy is spread evenly, there are vastly more arrangements that achieve that same average state. As a system evolves, it almost inevitably moves toward the configuration that can be realized in the greatest number of ways. Entropy increases because probability dominates behavior when many degrees of freedom are involved. This also explains why entropy is additive. If you combine two independent systems, the total number of microstates is the product of the microstates of each system. Taking the logarithm turns this multiplication into addition. Entropy becomes extensive. It scales with system size. This property is not arbitrary. It reflects the combinatorial nature of microscopic configurations. Entropy is often associated with disorder, but that language can be misleading. A perfectly shuffled deck of cards has high entropy, but so does a crystal at thermal equilibrium. What matters is not visual chaos, but the number of microscopic arrangements consistent with the macroscopic description. A system can look orderly and still have high entropy if many microstates produce the same ordered appearance. This precision matters because entropy is not a vague trend. It is a constraint. It limits what processes can occur. You can convert work into heat with perfect efficiency, but you cannot convert heat entirely into work without additional changes elsewhere. This asymmetry is not a technological limitation. It is a fundamental law. It applies regardless of scale, from laboratory systems to astrophysical objects. Entropy also plays a central role in defining equilibrium. A system in equilibrium is one that has reached a macrostate of maximum entropy, given its constraints. Once there, no further spontaneous change occurs at the macroscopic level. Microscopic motion continues, but it does not produce observable change. The system has exhausted its accessible configurations under the imposed conditions. This idea extends naturally to radiation. A cavity filled with electromagnetic radiation reaches a characteristic distribution of energy across frequencies. This distribution maximizes entropy while conserving total energy. The result is blackbody radiation, a spectrum that depends only on temperature. This phenomenon was one of the early clues that classical physics was incomplete, leading eventually to quantum theory. Yet entropy remained central even as the underlying description changed. In quantum mechanics, entropy acquires a new formulation, but its meaning persists. Instead of counting classical microstates, one counts quantum states consistent with macroscopic constraints. The entropy of a quantum system can be defined in terms of its density matrix. When a system interacts with its environment, information about its precise state becomes inaccessible and entropy increases. This does not require ignorance in a psychological sense. It reflects physical correlations that are no longer tracked. What matters here is that entropy continues to govern irreversibility. Even in quantum systems, processes that increase entropy are overwhelmingly favored. The arrow of time remains tied to entropy growth. This connection is not optional. It is observed in every domain where large numbers of degrees of freedom are involved. Entropy also sets bounds. There are limits to how much information can be stored in a physical system of given energy and size. These limits arise because information storage requires distinguishable states, and distinguishability is constrained by thermodynamics. These ideas are not speculative. They follow from combining statistical mechanics with quantum theory. At no point does entropy become subjective. It does not depend on what an observer knows or chooses to ignore. It depends on which degrees of freedom are physically accessible and which are not. When entropy increases, it is because information about microscopic details has become dispersed into correlations that cannot be practically recovered. This rigor is essential. Later, when entropy appears in gravitational contexts, its definition does not change. The same quantity that describes heat flow and equilibrium also appears when spacetime develops horizons. That fact is surprising, but it is not metaphorical. It is quantitative. For now, entropy stands as a deeply grounded physical quantity. It emerges from counting. It governs irreversibility. It defines equilibrium. It constrains what transformations are possible in nature. Nothing about it requires gravity. Nothing about it requires space-time curvature. And yet, when gravity is present, entropy refuses to stay confined to matter alone. Entropy also plays a subtle role in how information becomes inaccessible, even when the underlying laws remain reversible. When a system interacts with its surroundings, correlations spread outward, energy is exchanged. Degrees of freedom that were once tightly controlled become entangled with many others. Recovering the original microscopic state would require tracking every interaction in exact detail. In practice, this is impossible. The information is not destroyed, but it is dispersed. This distinction is important. The increase of entropy does not mean that the fundamental laws lose information. At the microscopic level, the equations remain reversible. What changes is accessibility. Information becomes distributed across so many degrees of freedom that it can no longer be reconstructed by any realistic process. Entropy growth reflects this loss of practical control, not a violation of physical law. Because of this, entropy can be understood as a measure of missing information about microscopic configurations. This interpretation does not rely on human ignorance. It relies on physical limitations. If two systems are correlated in ways that cannot be locally accessed, the entropy of each subsystem increases, even though the total system may remain in a pure state. This is a direct consequence of how physical interactions distribute information. These ideas become precise in quantum theory. A quantum system described by a density matrix has an entropy that quantifies how mixed its state is. When a system becomes entangled with its environment, its entropy increases. This increase is not subjective. It can be calculated. It can be measured indirectly through observable effects. It governs decoherence, the process by which quantum systems begin to behave classically. What matters for the broader picture is that entropy connects three domains. It links microscopic laws to macroscopic behavior. It links information to physical constraints. And it defines a direction of time without being built into the fundamental equations themselves. This makes entropy unlike most other quantities in physics. It is not tied to a specific force or interaction. It applies wherever many degrees of freedom are present. Entropy also introduces limits that cannot be engineered away. No matter how advanced a machine becomes, it cannot violate the second law. You cannot build a device that extracts unlimited work from a single heat reservoir. You cannot erase information without dissipating energy. These are not technological challenges waiting for solutions. They are boundaries imposed by the structure of physical law. At this stage, entropy remains firmly grounded in non-gravitational physics. It describes gases, solids, radiation, and quantum systems interacting with environments. It has nothing to say yet about space-time curvature or the motion of planets. Its domain is matter and energy, not geometry. And yet, the mathematical form of entropy and the way it imposes limits will soon appear in an unexpected place. When gravity is introduced into thermodynamic reasoning, something remarkable happens. Systems governed by space-time geometry begin to obey laws that look strikingly similar to the laws of heat and entropy. Horizons behave like thermodynamic surfaces. Areas take the place of volumes. Temperature emerges where none was expected. These results do not come from analogy or interpretation. They come from direct calculation. Before reaching that point, it is essential to keep entropy anchored to its original meaning. It is a count of possibilities. It is a measure of accessible configurations. It governs irreversibility because probability overwhelmingly favors certain macrostates over others. Nothing about this definition changes when gravity enters the picture. Entropy is not mysterious. What is mysterious is where it appears. The same quantity that limits engines and governs heat flow also constrains black holes and horizons. That convergence is not assumed. It is discovered. And it forces gravity and thermodynamics into the same conversation. Black holes were not introduced to physics as exotic objects or as speculative ideas. They emerged naturally from the equations of general relativity. When Einstein's equations are applied to a sufficiently compact concentration of mass and energy, they predict regions of spacetime where curvature becomes so extreme that ordinary notions of distance and time fail. These regions are not separated from the rest of the universe by walls or barriers. They are defined by geometry alone. At the boundary of a black hole lies an event horizon. This surface is not a physical object. It has no thickness and no material structure. It is a geometric boundary that separates events that can influence distant observers from those that cannot. Once something crosses this boundary, no signal it emits can ever reach the outside world. Light itself is trapped, not because it slows down, but because all possible paths forward in time point inward. From the outside, the event horizon appears calm and featureless. Nothing dramatic happens at the moment an object crosses it. The object does not encounter a wall or a sudden force. Locally, the laws of physics remain unchanged, yet globally, information about that object is cut off. The horizon introduces a limit on what can be known and what can be observed. This is where thermodynamics enters the story in an unexpected way. In the early 1970s, physicists noticed a striking analogy. Black holes obey laws that closely resemble the laws of thermodynamics. The surface area of the event horizon never decreases in classical general relativity, much like entropy never decreases in isolated systems. When black holes merge, the total horizon area increases. This resemblance was not superficial. It suggested a deeper connection. Jacob Bekenstein proposed that black holes should be assigned an entropy proportional to the area of their event horizons. This was a radical idea. Entropy had always been associated with microscopic degrees of freedom. with atoms and molecules. A black hole, by contrast, seemed to erase all information about what formed it. How could an object defined by only mass, charge, and rotation possess entropy? The proposal was not philosophical. It was motivated by consistency. If you drop a box of matter with entropy into a black hole, that entropy appears to disappear from the observable universe. If black holes have no entropy, the second law of thermodynamics would be violated. To preserve the law, black holes must carry entropy of their own. The only quantity that behaved in the right way was the horizon area. This idea gained decisive support when Stephen Hawking made a discovery that surprised even him. By applying quantum field theory in curved spacetime, he showed that black holes are not completely black. They emit radiation. This radiation arises from quantum fluctuations near the event horizon. To a distant observer, the black hole behaves like a thermal object with a well-defined temperature. This result changed everything. A temperature implies entropy. Hawking's calculation fixed the proportionality constant in Bekenstein's proposal. The entropy of a black hole is proportional to the area of its horizon divided by fundamental constants. The relationship is precise. It is not adjustable. It does not depend on the type of black hole or the details of what fell into it. What makes this result extraordinary is not just that black holes have entropy. It is how that entropy scales. In ordinary systems, entropy scales with volume. Double the size of a box of gas, and you roughly double the entropy. For black holes, entropy scales with surface area. Double the radius of the horizon, and the entropy increases with the square of that radius. The degrees of freedom appear to live on the boundary, not in the interior. This area scaling is not a metaphor. It is a calculated result. It holds across different types of black holes. It survives detailed analysis. It suggests that the fundamental description of gravitational systems may be radically different from that of ordinary matter. At the same time, caution is essential. The calculation of black hole entropy relies on well-established physics, but it does not explain the microscopic origin of that entropy. It tells us how much entropy a black hole has, not what the underlying states are. The result is robust, but its interpretation remains open. Black hole thermodynamics does not replace general relativity. It extends it. It reveals that when gravity, quantum theory, and thermodynamics intersect, new structures appear. Horizons behave like thermodynamic systems. Geometry acquires temperature. Area becomes a measure of information capacity. None of this requires speculation beyond established frameworks. The equations are clear. The results are consistent, yet their implications are profound. Gravity, which began as geometry, now carries thermodynamic properties. Entropy, which began as a count of microscopic configurations, now appears encoded in spacetime itself. The appearance of temperature and entropy in black hole physics forces a reconsideration of what these quantities really mean. A black hole, in classical general relativity, is defined entirely by its mass, rotation, and charge. It has no internal structure that can be probed from the outside. Everything else about the matter that formed it is hidden behind the event horizon. And yet, when quantum effects are included, this seemingly simple object behaves like a thermodynamic system. Hawking radiation is extremely weak for astrophysical black holes. For a black hole with the mass of the Sun, the temperature is far colder than the background radiation of the universe. Such a black hole absorbs more energy than it emits and grows over time. But the existence of the radiation matters far more than its strength. It shows that horizons are not passive boundaries. They interact with quantum fields in a precise and calculable way. From the perspective of a distant observer, the radiation appears thermal. It carries no information about the details of what fell into the black hole. The spectrum depends only on the black hole's mass, rotation, and charge. This reinforces the idea that black holes erase information, at least in their outgoing radiation. That conclusion, however, creates a tension with quantum theory, which demands that information be preserved. This tension is known as the black hole information problem. If a black hole forms from matter in a specific quantum state and then evaporates completely through thermal radiation, the final state appears to be independent of the initial one. Information seems to be lost. Quantum mechanics does not allow this. The problem is not philosophical, it is mathematical. It arises from applying two well-tested theories in the same regime. What matters here is not the resolution of the information problem, which remains an active area of research, but the role entropy plays in creating it. The entropy of a black hole is enormous. It vastly exceeds the entropy of the matter that formed it. This suggests that the horizon encodes an enormous number of degrees of freedom, far more than would be expected if those degrees of freedom were distributed throughout the volume. The proportionality between entropy and area introduces a new kind of limit. There is a maximum amount of entropy, and therefore a maximum amount of information that can be contained within a given region of space. If you try to pack more information into that region, it collapses into a black hole. The limiting factor is not volume, it is surface area. This idea is not an interpretation layered on top of black hole physics. It follows directly from combining thermodynamics with gravity. The event horizon acts as a boundary beyond which information is inaccessible. The entropy measures that inaccessibility quantitatively. The more area the horizon has, the more information it can hide. What is striking is that the entropy is finite. Even though the interior of a black hole may be large or even infinite in certain coordinate descriptions, the entropy depends only on the horizon area. This suggests that the fundamental degrees of freedom associated with gravity are not located in the interior in the usual sense. They are associated with the boundary. At this point, nothing has been assumed about holography or emergent spacetime. The conclusion follows from established results. Black holes obey thermodynamic laws. They have temperatures. They have entropies. Their entropy scales with area, not volume. These facts are robust. The analogy with ordinary thermodynamics goes further. Black holes obey versions of the first, second, and third laws. Changes in mass correspond to changes in energy. Horizon area plays the role of entropy. Surface gravity corresponds to temperature. These relationships are precise, not symbolic. They hold across different black hole solutions. This convergence between gravity and thermodynamics was not anticipated when general relativity was formulated. It emerged only when quantum effects were considered near horizons. It suggests that space-time geometry carries microscopic degrees of freedom, even if their nature is not yet understood. Entropy counts something. The question is what? Importantly, this does not mean spacetime is made of atoms in the usual sense. The analogy with matter must be handled carefully. What it means is that spacetime, when constrained by horizons, behaves as if it has an underlying statistical description. The entropy is real. The temperature is real. The radiation is real. Black hole thermodynamics therefore marks the first place where gravity and entropy are unavoidably linked. Not through metaphor, not through analogy, through equations that survive scrutiny. Gravity, once described purely as geometry, now exhibits thermodynamic behavior. Entropy, once confined to matter and radiation, now appears tied to spacetime itself. This does not yet tell us how gravity emerges or whether spacetime is fundamental, but it tells us that any deeper theory of gravity must explain why horizons carry entropy and why that entropy scales with area. This requirement is not optional. It is imposed by observation and calculation. The implications of black hole thermodynamics extend beyond black holes themselves. Event horizons are not unique to collapsed stars. Any situation in which space-time geometry creates a boundary that limits observation shares similar features. Accelerated observers experience horizons. Expanding universes possess horizons. In each case, Horizons introduce limits on information and access, and in each case, thermodynamic concepts reappear. An observer accelerating through empty space will perceive a horizon behind them. Regions of spacetime become permanently inaccessible. Remarkably, quantum field theory predicts that such an observer will detect a thermal bath of particles, even though an inertial observer detects none. Temperature emerges purely from geometry and motion. This effect is small, but its existence reinforces a central lesson. Horizons and thermodynamics are inseparable. Cosmology provides another example. In an expanding universe, there are regions from which light will never reach a given observer. These cosmological horizons also carry entropy. The entropy again scales with area. The pattern repeats. Wherever spacetime geometry imposes a limit on what can be observed, entropy appears. This repetition suggests that entropy is not merely a property of matter sitting in spacetime. It is connected to the structure of spacetime itself when access is restricted. The entropy counts the degrees of freedom hidden behind horizons. What those degrees of freedom are remains unknown, but their existence is not optional. Without them, the laws of thermodynamics would fail. At the same time, it is important to avoid overinterpretation. The presence of entropy does not by itself explain gravity. It does not tell us that spacetime is made of information or that geometry is an illusion. What it tells us is more restrained and more demanding. Any complete description of gravity must account for the thermodynamic behavior of horizons. It must explain why area, not volume, governs entropy. It must preserve information in a way consistent with quantum theory. Black hole thermodynamics therefore acts as a constraint on deeper theories. It narrows the range of possibilities. Whatever gravity ultimately is, it cannot ignore entropy. Whatever spacetime ultimately is, it must accommodate information bounds that scale with area. At this stage, the story remains grounded. Nothing has been assumed beyond general relativity, quantum field theory in curved spacetime, and thermodynamics. These are well-established frameworks. The results they produce are not speculative. They are consequences. The convergence of gravity and entropy at horizons does not answer the deepest questions. It sharpens them. Why should geometry behave thermodynamically? Why should information capacity be limited by surface area? Why should spacetime itself appear to carry entropy? These questions do not arise from imagination. They arise from calculation. They force physicists to consider the possibility that spacetime, like temperature or pressure, may not be fundamental. It may be an effective description that emerges when deeper degrees of freedom are viewed at large scales. But that possibility remains a question, not a conclusion. Before exploring proposals that attempt to answer it, one more ingredient must be introduced carefully and precisely: information. Not as a metaphor, not as a slogan, but as a physical quantity with measurable limits. Information is often treated as something abstract, something that belongs to communication theory or computer science rather than to the physical world. But in modern physics, information is not optional, and it is not merely conceptual. It is constrained by energy, by space, and by the laws that govern physical systems. Information has weight in the logic of nature, even when it has no mass in the ordinary sense. To understand why information becomes unavoidable, it helps to return to a simple idea. Any physical system that can be in different distinguishable states can store information. A switch can be on or off. A particle can be here or there. A quantum system can occupy one state or another. Information is encoded in physical differences, and those differences require resources. They require energy to create, space to separate, and time to manipulate. This immediately places limits on information storage. You cannot store an unlimited amount of information in a finite region of space with finite energy. If you try, the system reacts. Heat is generated. Entropy increases. And if energy density becomes too large, gravity intervenes. The system collapses. These limits were made precise through the work of Jacob Bekenstein. He asked a careful question. Given a region of space with a fixed size and a fixed total energy, what is the maximum amount of information that region can contain? The answer is not arbitrary. It follows from combining quantum mechanics, thermodynamics, and relativity. The result is known as the Bekenstein bound. It states that there is an upper limit to the entropy, and therefore the information, that can be stored within a given region. If you exceed that limit, the region must collapse into a black hole. At that point, the maximum entropy is given by the area of the resulting horizon, not the volume of the region. This is not an assumption. It is a consistency requirement. If more information could be stored without collapse, the second law of thermodynamics would be violated when matter falls into a black hole. The bound preserves both thermodynamics and gravity at once. What is remarkable is how general this result is. It does not depend on the details of the matter inside the region. It does not depend on whether the information is stored in particles, fields, or quantum states. It depends only on total energy and size. Information, in this sense, becomes a universal physical quantity, subject to universal limits. This changes how information must be treated. It is no longer something that floats freely above physics. It is constrained by the same laws that constrain motion and energy. You cannot erase information without a cost. You cannot compress it arbitrarily. You cannot hide it without consequence. Quantum mechanics reinforces this picture. In quantum theory, information is tied to the distinguishability of states. Two states that are not perfectly distinguishable cannot encode a full bit of information. Noise, uncertainty, and entanglement all limit how much information can be extracted. These limitations are not technological. They are fundamental. The combination of quantum mechanics and gravity sharpens these constraints further. As you attempt to localize information more precisely, you require higher energies. Higher energies curve spacetime more strongly. At some point, the attempt to localize information creates a horizon. The information becomes hidden behind it. Geometry enforces the bound. This is why information loss becomes such a serious issue in black hole physics. If information truly disappeared, quantum mechanics would fail. But if it is preserved, it must be stored somewhere consistent with the entropy bounds. The horizon becomes the only available place. At this point, nothing has been said about holography as a principle. Nothing has been assumed about spacetime being an illusion. What has been established is more modest and more solid. Information is physical. It is bounded. And gravity enforces those bounds through geometry. This realization reshapes how spacetime itself is viewed. If the maximum information content of a region is proportional to its surface area, then volume is not the relevant measure of degrees of freedom. The bulk may not carry independent information beyond what the boundary allows. This does not yet tell us how information is stored or processed by spacetime. It tells us only that there is a limit, and that the limit is geometric. Area replaces volume as the controlling factor. That fact alone is enough to challenge long-held intuitions about space. Before any claims are made about holography or emergent geometry, these bounds must be taken seriously. They are not speculative. They arise from demanding consistency between gravity, thermodynamics, and quantum mechanics. Any deeper theory must respect them. Once information is treated as a physical quantity, its relationship to entropy becomes unavoidable. Entropy and information are not separate concepts stitched together by analogy. They are mathematically linked. Entropy measures how many microscopic configurations correspond to a given macroscopic description. Information measures how much specification is required to single out one configuration from that set. When entropy is high, more information is missing. When entropy is low, more information is specified. This connection becomes especially clear when information is erased. Erasing information is not simply forgetting, it is a physical process. When a memory is reset, the system is forced into a smaller set of possible states. The missing distinctions are transferred to the environment as heat. This process increases entropy elsewhere. No physical system can erase information without paying this cost. This is not a design flaw, it is a law. The energy required to erase information is small, but it is not zero. The cost depends on temperature. At higher temperatures, erasure produces more entropy. At lower temperatures, less. But the cost never vanishes. This establishes a direct link between information, energy, and entropy. Information processing is constrained by thermodynamics in the same way as engines and refrigerators. These limits are not confined to classical systems. In quantum mechanics, information is tied to the structure of states and their correlations. A quantum system can store information in superpositions and entanglement, but extracting that information is limited by measurement constraints. When a quantum system becomes entangled with its environment, information about its precise state spreads out. Locally, that information is lost. Entropy increases. Importantly, the total information is not destroyed, it is redistributed. This distinction becomes crucial when gravity is involved. If information is conserved globally but inaccessible locally, entropy increases without violating fundamental laws. Horizons provide a geometric mechanism for this separation. They divide spacetime into regions that cannot exchange information. This is why horizons are so central to information bounds. A horizon is not a material barrier. It is a limit imposed by geometry. It defines what can be known by a given observer. When information crosses a horizon, it does not cease to exist, but it becomes inaccessible. Entropy accounts for this loss of access. The Bekenstein bound can be understood in this way. It is not merely a limit on storage capacity. It is a statement about accessibility. You cannot pack more distinguishable states into a region than its boundary allows without creating a horizon that hides those states. Geometry intervenes to enforce the limit. What makes this remarkable is that the bound depends only on area, not on the complexity of the contents. Whether the information is stored in particles, fields, or quantum correlations does not matter. The boundary determines the maximum. This universality suggests that the bound is not an accident of particular models. It reflects something fundamental about how spacetime constrains information. At this point, a pattern is difficult to ignore. Entropy scales with area in black holes. Information storage is bounded by area. Horizons appear whenever access is limited. Geometry enforces thermodynamic laws. These facts emerge independently from different lines of reasoning, yet they converge on the same conclusion. Boundaries matter more than volumes. Still, restraint is essential. These results do not yet imply that the interior of spacetime is unreal or that physics happens only on surfaces. They tell us that there are limits, not mechanisms. They impose constraints without providing a constructive model of how information is encoded. The next step is therefore not to leap to conclusions, but to introduce the framework that attempts to formalize these constraints. This framework does not claim to be proven. It does not claim to describe reality in all circumstances. It claims only to provide a consistent way of understanding why area appears again and again in gravitational systems. That framework is known as the holographic principle. It emerges not from speculation, but from taking information bounds seriously and asking what kind of description could satisfy them without contradiction. The holographic principle does not begin as a claim about how the universe works. It begins as a response to a problem. If the maximum entropy in a region scales with surface area, then any theory that assigns independent degrees of freedom to every point in the volume will overcount. Such a theory would predict more possible states than gravity allows. The conflict is not subtle, it is quantitative. To resolve this, one must accept at least one of two possibilities. Either the volume description is incomplete, or the degrees of freedom it counts are not all independent. The holographic principle takes the second option seriously. It proposes that all the information contained in a region of space can be described by degrees of freedom defined on its boundary. This does not mean the interior does not exist. It means the interior description may be redundant. This proposal is deliberately cautious. It does not say that spacetime is literally a projection, or that physics happens only on surfaces. It says that the number of independent degrees of freedom required to describe a region grows like area, not volume. That statement alone is enough to satisfy the information bounds imposed by gravity. What makes this idea compelling is that it does not arise from a single argument. It appears again and again in different contexts. Black hole entropy demands it. Information bounds require it. Attempts to reconcile quantum mechanics with gravity repeatedly encounter it. The principle acts like a convergence point for otherwise independent lines of reasoning. At the same time, the holographic principle is not a law of nature in the same sense as the second law of thermodynamics or Einstein's field equations. It is a framework. It provides guidance. It constrains how theories can be constructed without contradiction. Where it applies and how literally it should be taken remain open questions. There are specific settings where holography is mathematically precise. In those cases, a gravitational theory in a higher dimensional spacetime can be exactly equivalent to a non-gravitational theory defined on a lower dimensional boundary. Every observable in one description corresponds to an observable in the other. Nothing is lost. Nothing is added. The equivalence is exact. However, these examples rely on special conditions. They involve idealized spacetimes with specific symmetries. They do not describe the universe we observe in full generality. Extending these results beyond their original domain remains an active area of research. What matters here is not the details of those constructions, but the lesson they teach. It is possible, at least in principle, for a theory of gravity to be fully encoded in a lower dimensional description without gravity. Geometry can emerge from non-geometric data. Spacetime can be reconstructed from information-theoretic relationships. This does not mean spacetime is an illusion. It means spacetime may be an effective description, much like temperature or pressure. These quantities are real. They are measurable. They obey precise laws. But they are not fundamental in the same way as the microscopic degrees of freedom from which they arise. If spacetime is similar, then gravity as geometry may itself be an emergent phenomenon. The curvature of spacetime would reflect the collective behavior of underlying degrees of freedom governed by information and entropy. This idea is powerful, but it remains a hypothesis. It must be tested against known physics. It must reproduce general relativity where it has been confirmed. And it must not violate established principles. At this stage, nothing has been claimed beyond what the bounds require. Information is physical. It is limited. Gravity enforces those limits. Area, not volume, controls capacity. These facts alone motivate holographic thinking. They do not force any particular interpretation. The next step is therefore to examine how geometry itself might be related to information in a precise way, not as a metaphor, not as philosophy, but through explicit models that show how distances and curvature can be reconstructed from patterns of correlation. This is where quantum information theory enters the discussion. The holographic principle is often misunderstood because of the imagery its name evokes. It does not claim that the universe is a literal projection, nor does it suggest that reality is an illusion in any everyday sense. The term holographic is technical. It refers to a relationship between descriptions, not to a visual effect. At its core, the principle addresses a mismatch between how many degrees of freedom gravity allows and how many conventional theories attempt to assign. In ordinary quantum field theory, degrees of freedom are associated with every point in space. If you divide a region into smaller and smaller pieces, the number of independent variables grows with volume. This works well when gravity is negligible. But when gravity is included, this counting fails. The entropy bounds imposed by black holes show that there is a maximum number of states that can fit inside a region, and that maximum scales with surface area. Any theory that ignores this limit predicts states that cannot physically exist. The holographic principle proposes a way out. It suggests that the complete physical description of a region can be encoded on its boundary with no loss of information. The interior description is not denied, but it is not independent. It may contain redundancy, much like multiple coordinate descriptions of the same geometry. The principle does not replace spacetime. It constrains how spacetime can be described consistently. This idea did not arise from philosophical speculation. It emerged from attempting to preserve both quantum mechanics and thermodynamics in the presence of gravity. Black hole entropy forced physicists to confront the fact that information capacity is limited. The holographic principle is a response to that fact, not an embellishment of it. There are specific contexts where holography is not just an idea, but a precise mathematical statement. In these cases, a theory that includes gravity in a higher dimensional spacetime can be exactly equivalent to a theory without gravity defined on a lower dimensional boundary. Every physical quantity in one description has a corresponding quantity in the other. The equivalence is complete. Nothing is approximate. These examples are highly controlled. They rely on idealized spacetimes with special symmetries. They do not describe the universe in its full complexity, but they demonstrate something crucial. It is possible for geometry to emerge from non-geometric degrees of freedom. Distances, curvature, and gravitational dynamics can be reconstructed from information defined on a boundary. This does not mean that spacetime is fundamentally unreal. It means that spacetime may be similar to other emergent quantities in physics. Temperature is not fundamental. It emerges from microscopic motion. Pressure is not fundamental. It emerges from momentum transfer. Yet both are real, measurable, and indispensable. Geometry may belong to this same category. What makes the holographic principle compelling is not that it answers all questions, but that it satisfies known constraints. It respects entropy bounds. It preserves information. It reproduces gravitational dynamics where it has been tested. It does not violate established laws. Where it applies, it works. At the same time, it is essential to remain cautious. The holographic principle is not universally proven. Outside of specific settings, it remains a conjecture. There is no experimental confirmation that our universe admits a complete holographic description. There is no direct evidence that all spacetime degrees of freedom reside on a boundary. What can be said with confidence is more limited and more precise. Any consistent theory of quantum gravity must respect holographic bounds. Whether or not holography is the final framework, the lessons it encodes are unavoidable. Information capacity is finite. Area matters. Volume cannot be freely populated with independent states. The holographic principle therefore functions as a guide rather than a verdict. It shapes how theories are constructed. It warns against certain assumptions. It suggests that geometry and information are more deeply connected than classical intuition allows. This connection becomes sharper when one asks how geometry might actually arise from information. Not in principle, but in detail. How does distance emerge? How does curvature emerge? How does space-time connectivity arise from correlations? These questions are not answered by holography alone. They require tools from another field. Those tools come from quantum information theory, where correlations, entanglement, and entropy are treated with mathematical precision. Only by introducing those tools can the relationship between information and geometry be examined without metaphor. The challenge that follows the holographic principle is not philosophical but technical. If a lower dimensional description can fully encode a higher dimensional gravitational system, then the structure of spacetime itself must be reflected in patterns of information. Geometry cannot be an independent input. It must be reconstructed. The question becomes precise. What features of information correspond to distance, to curvature, and to connectivity? In ordinary geometry, distance is a primitive concept. Two points are separated by a length that can be measured with a ruler or inferred from the time it takes light to travel between them. In a holographic description, there is no spacetime in which such rulers exist. The only available quantities are correlations between degrees of freedom. If geometry is to emerge, it must be encoded in those correlations. This idea can be explored without speculation. In quantum information theory, correlations are quantified with exact measures. One of the most important is entanglement entropy. When two subsystems are strongly entangled, measurements on one carry information about the other. When entanglement is weak, the systems behave more independently. This is not a metaphor. It is a calculable quantity. What researchers discovered is that patterns of entanglement can be used to reconstruct geometric relationships. Subsystems that are highly entangled behave as if they are close together in an emergent space. Subsystems with little entanglement behave as if they are far apart. Distance, in this sense, becomes a measure of correlation strength rather than a primitive coordinate. This does not mean that space is made of entanglement. It means that geometry can be inferred from entanglement structure. In specific holographic models, the amount of entanglement between regions of the boundary determines the area of certain surfaces in the bulk geometry. These surfaces are not arbitrary. They satisfy precise mathematical conditions. The correspondence is exact within the model. What is striking is that the same area scaling that appears in black hole entropy reappears here. Entanglement entropy scales with the size of the boundary between regions, not with their volume. This mirrors the gravitational result. Area continues to dominate. Information continues to obey geometric limits. From this perspective, space-time connectivity becomes an information-theoretic concept. Regions of space remain connected because the underlying degrees of freedom are entangled. If entanglement is reduced, connectivity weakens. In extreme cases, space-time can fragment. These are not visual metaphors. They are consequences of precise calculations within controlled models. At the same time, limits must be emphasized. These results do not show that all space-time in our universe is built from entanglement in this way. They show that such a construction is possible and consistent in certain theoretical settings. The models are simplified. They rely on symmetries and ideal conditions that may not apply universally. Nevertheless, the lesson is powerful. Geometry need not be fundamental to be real. It can arise as a large-scale description of deeper information-theoretic relationships. Just as temperature emerges from molecular motion, distance and curvature may emerge from patterns of quantum correlation. This view does not replace general relativity. It seeks to explain why general relativity works. If space-time geometry is emergent, then Einstein's equations may be effective equations, similar to the equations of fluid dynamics. They would describe collective behavior without revealing the microscopic details. The holographic principle does not demand this interpretation, but it allows it. It opens the door to a class of theories in which gravity is not a fundamental interaction, but a macroscopic manifestation of information dynamics. Whether this door leads to our universe remains unknown. What is clear is that the holographic framework reshapes the questions physicists ask. Instead of asking what spacetime is made of, they ask how spacetime can be reconstructed. Instead of asking where gravity comes from, they ask what conditions make geometry behave gravitationally. These questions do not have final answers yet, but they are sharply defined. They are constrained by entropy bounds, by black hole thermodynamics, and by quantum information theory. Any proposal that claims to explain gravity must pass these tests. At this point, the holographic principle has done its job. It has reframed the problem without overstepping the evidence. It has shown that gravity and geometry are compatible with an information-based description. It has not claimed that this description is unique or complete. To move further, one must examine how information behaves in quantum systems in more detail. How entanglement is structured, how it spreads, how it changes under dynamics. These questions belong to quantum information theory, and they provide the next piece of the puzzle: Quantum information theory was not developed to explain gravity. It arose from attempts to understand the limits of computation, communication, and measurement in quantum systems. Yet the tools it provides turn out to be unexpectedly well-suited for addressing questions about space-time. This is not because space-time is assumed to be information, but because information theory offers a precise language for describing correlations, limits, and structure without presupposing geometry. In quantum mechanics, the state of a system is described by a wave function, or, more generally, by a density matrix. When a system is composed of parts, its overall state cannot always be written as a simple combination of the states of those parts. The parts can be entangled. Entanglement is not a force or a signal. It is a correlation that cannot be reduced to classical statistics. Measurements performed on one part of an entangled system constrain the possible outcomes of measurements on the other, even when the parts are separated. Entanglement has a measurable quantity associated with it. This quantity is entanglement entropy. Given a system divided into two regions, entanglement entropy measures how much information about one region is inaccessible when only the other is observed. It is defined with mathematical precision. It is not subjective. It depends only on the structure of the quantum state. What makes entanglement entropy remarkable in the present context is how it scales. In many quantum systems, entanglement entropy does not scale with volume. It scales with the size of the boundary between regions. This is known as an area law. The degrees of freedom that contribute to entanglement are concentrated near boundaries, not spread uniformly throughout space. This behavior is robust. It appears in ground states of many quantum systems and persists across different models. This area scaling mirrors what is seen in black hole entropy. Once again, surface area replaces volume as the controlling quantity. This parallel is not coincidental. It suggests that the same underlying constraints govern both quantum correlations and gravitational horizons. Information is limited not by how much space is available, but by how regions are connected. In certain theoretical frameworks inspired by holography, this connection becomes explicit. The entanglement entropy of regions in a lower dimensional quantum system corresponds directly to geometric quantities in a higher dimensional spacetime description. Surfaces in the emergent geometry are determined by patterns of entanglement. Change the entanglement, and the geometry changes. These constructions do not require assuming spacetime at the outset. Geometry appears as a derived concept. Distances correspond to the strength of correlations. Connectivity corresponds to entanglement. Smooth geometry corresponds to smoothly varying entanglement patterns. Where correlations weaken, geometry stretches or pinches. It is important to be precise about what this does and does not mean. These results do not imply that spacetime is literally made of qubits or that entanglement is a substance. They show that certain geometric relationships can be reconstructed from information theoretic data. The mapping is mathematical, not material. The strength of this approach lies in its restraint. It does not discard general relativity. It explains why general relativity might emerge as an effective description. If spacetime geometry reflects the collective behavior of underlying quantum correlations, then Einstein's equations could arise as large-scale constraints on information flow and entanglement structure. At the same time, there are limits. These models rely on idealized systems. They require specific symmetries and boundary conditions. Extending them to realistic cosmological spacetimes remains an open problem. No experiment has yet tested whether spacetime geometry in our universe is encoded in this way. What can be said with confidence is narrower and more solid. Quantum information theory provides a consistent language for discussing how geometry could emerge without violating known laws. It respects entropy bounds. It preserves unitarity. It reproduces gravitational behavior where it has been shown to apply. This convergence does not prove that spacetime is emergent. It shows that emergence is possible. It transforms the question from metaphysical speculation into a technical problem. How do patterns of quantum correlation give rise to classical geometry? Under what conditions does gravity appear? When does this description fail? These questions mark the boundary between what is known and what is being explored. They do not overturn established physics. They sit on top of it, constrained by it, and accountable to it. The relationship between entanglement and geometry becomes clearer when one considers how changes in quantum states affect large-scale structure. In ordinary materials, altering microscopic interactions can change macroscopic properties like rigidity or conductivity. In holographic-inspired models, altering entanglement changes geometry itself. When entanglement between regions is reduced, the effective distance between those regions increases. When entanglement is removed entirely, the regions become disconnected. Geometry reflects correlation. This insight reframes what distance means at a fundamental level. Distance no longer needs to be assumed as a primitive quantity. It can be inferred. Two subsystems are close if they share strong quantum correlations. They are far apart if those correlations are weak. Spacetime becomes a bookkeeping device that summarizes how information is distributed. The same reasoning applies to curvature. In general relativity, curvature reflects how spacetime responds to energy and momentum. In an information-based picture, curvature reflects how entanglement patterns vary across the system. Uniform entanglement corresponds to flat geometry. Gradients in entanglement correspond to curvature. Concentrations of energy correspond to disruptions in correlation structure. This correspondence is not guessed. In controlled models, it can be calculated. Small perturbations in quantum states produce changes in entanglement entropy that obey equations formally equivalent to Einstein's equations in the emergent geometry. This result is striking because it suggests that gravitational dynamics may arise from consistency conditions on information flow rather than from a fundamental force. Again, caution is essential. These results do not claim that gravity is nothing but entanglement. They show that gravity can be described in terms of entanglement in certain regimes. They do not establish that this description is unique or complete. They do not eliminate the need for spacetime as an effective concept. What they do establish is that geometry and information are deeply linked. Geometry is not arbitrary. It reflects constraints on how information can be organized. Entropy bounds, area laws, and holographic limits all point in the same direction. Spacetime cannot support unlimited independent degrees of freedom. Its structure is shaped by information-theoretic rules. This perspective also clarifies why gravity resists quantization. If gravity is not a fundamental interaction, but an emergent description, then attempting to quantize it directly may be misguided. One does not quantize temperature. One explains temperature by quantizing molecules. Similarly, one might not quantize geometry itself, but rather the underlying degrees of freedom from which geometry emerges. This does not diminish gravity, it contextualizes it. General relativity remains accurate and indispensable at macroscopic scales. Its equations describe how geometry behaves once it has emerged. They do not need to describe the microscopic origin of that geometry to be valid. At this point, the connection between quantum information and geometry is established as a research program, not a conclusion. It provides a coherent way to think about emergence without violating known physics. It explains why entropy and area appear together. It explains why horizons behave thermodynamically. It explains why information bounds are geometric. What remains is to ask whether gravity itself could be understood as a consequence of entropy and information flow, rather than as a fundamental interaction. This idea has been proposed, explored, and criticized. It must be treated with care. That proposal is known as entropic gravity. The idea that gravity might arise from entropy does not come from a desire to simplify physics or to replace general relativity. It arises from a pattern that becomes difficult to ignore. Gravity behaves geometrically. Horizons carry entropy. Information is bounded by area. Geometry responds to limits on access. Taken together, these facts invite a careful question. Could gravity itself be a macroscopic consequence of underlying statistical behavior? Entropic forces are not speculative inventions. They are well known in statistical physics. An entropic force does not arise from a fundamental interaction like electromagnetism. It arises from the tendency of systems to move toward configurations with higher entropy. The force is effective rather than fundamental. It reflects probability, not attraction. A simple example makes this clear. Consider a polymer molecule immersed in a thermal environment. When stretched, the polymer experiences a restoring force. This force does not come from a microscopic spring. It arises because there are many more microscopic configurations corresponding to the coiled state than to the stretched state. The system resists stretching because entropy decreases. The force is statistical in origin, but it is measurable and real. Entropic forces obey precise laws. They depend on temperature. They depend on entropy gradients. They disappear when entropy does not change. No new interactions are introduced. The force emerges from counting configurations. This concept is well established and experimentally verified in many physical systems. The proposal known as entropic gravity asks whether gravity could be similar. It suggests that gravitational acceleration might arise from entropy gradients associated with information and horizons. In this view, matter moves not because spacetime pulls on it, but because configurations with higher entropy are favored. Gravity would then be an emergent phenomenon, not a fundamental interaction. One influential version of this idea was proposed by Erik Verlinde. The proposal does not deny general relativity. It attempts to recover gravitational behavior from thermodynamic and information theoretic assumptions. The derivations are intended to reproduce familiar gravitational laws under specific conditions, not to replace established results outright. The starting point is modest. It assumes that information is associated with surfaces, that entropy changes when matter moves, and that temperature can be defined through horizon-like constructions. From these assumptions, an effective force law resembling Newtonian gravity can be derived. The force arises from entropy gradients rather than from a fundamental field. It is important to be precise about what this does and does not show. Recovering Newtonian gravity in a limited regime does not establish a new theory of gravity. Newtonian gravity itself is an approximation. Any proposal must reproduce general relativity, not merely its low energy limit. Entropic gravity proposals attempt this to varying degrees with mixed success. One point of contact with established physics is the equivalence between acceleration and temperature. An accelerating observer perceives a thermal environment even in empty space. This is a calculated result of quantum field theory. Entropic gravity proposals use this fact to associate temperature with acceleration, providing a thermodynamic ingredient without introducing new physics. From there, the argument proceeds carefully. If moving a particle changes the entropy associated with a horizon, and if temperature is defined, then a force can be associated with that entropy change. This force has the right form to resemble gravity under specific assumptions. The appeal of this approach lies in its economy. It uses known physics. It does not introduce new particles or fields. It aligns with the idea that geometry and gravity may be emergent. But appeal is not evidence. The proposal must be judged by consistency, completeness, and agreement with observation. Criticisms of entropic gravity are substantial and serious. One major concern is that the derivations rely on assumptions whose physical justification is unclear outside idealized settings. Another is that extending the approach to fully relativistic regimes is difficult. Recovering Einstein's field equations in general spacetimes remains an open challenge. There are also questions about dynamics. Entropic forces typically depend on equilibrium assumptions. Gravity operates far from equilibrium in many situations. Whether entropy-based reasoning can capture such dynamics is not established. Additionally, the role of time in entropic gravity proposals is not always clear. For these reasons, entropic gravity remains a hypothesis. It is not a theory in the same sense as general relativity. It has not been experimentally confirmed. It has not replaced existing frameworks. It serves as a conceptual probe, testing how far thermodynamic reasoning can be pushed in gravitational contexts. What matters is not whether entropic gravity is correct. What matters is what it reveals. It highlights the deep connections between gravity, entropy, and information. It forces clarity about assumptions. It shows which features of gravity might be emergent and which must be fundamental. Entropic gravity does not overturn established physics. It operates within it. It does not claim certainty. It raises a disciplined question. Could gravity be an effective manifestation of statistical behavior tied to information and entropy? That question remains open. If gravity were purely an entropic effect, its behavior would ultimately depend on how entropy changes when matter moves. That dependence must be universal. It must not depend on the internal composition of objects. It must reproduce the equivalence principle, one of the most precisely tested features of gravity. All objects, regardless of their mass or makeup, fall in the same way when other forces are negligible. Any entropic explanation must account for this fact without exception. Supporters of entropic gravity argue that universality can arise naturally. If the entropy change associated with displacement depends only on position and not on the properties of the object, then all objects experience the same effective acceleration. In this view, mass does not determine how strongly an object responds to gravity. It determines how much energy is involved in the entropy balance, while the geometric response remains the same. This reasoning is appealing, but it remains incomplete. In known entropic systems, forces depend on temperature and entropy gradients that are defined relative to specific environments. Gravity, by contrast, acts universally and persists even in extreme conditions. Whether entropy gradients with the required properties exist in all gravitational settings is not yet demonstrated. Another challenge arises when one considers relativistic gravity. General relativity is not merely a force law, it is a dynamical theory of space-time geometry. The curvature evolves. Gravitational waves propagate. Space-time responds to changing energy distributions. Any emergent description must reproduce this full structure, not just static forces. Some work has shown that under restricted conditions, equations resembling Einstein's equations can be derived from thermodynamic arguments applied to local horizons. These derivations are mathematically consistent, but they rely on assumptions about equilibrium and locality that may not hold universally. They suggest a deep connection, but they stop short of a complete theory. There is also the question of prediction. A new framework must do more than reproduce known results. It must make new predictions, or offer clearer explanations where existing theories struggle. So far, entropic gravity has not produced unambiguous, testable predictions that distinguish it from general relativity. Where predictions have been proposed, they remain controversial and not universally accepted. This does not mean the idea is without value. Entropic gravity serves as a diagnostic tool. It exposes which aspects of gravity might arise from general principles like entropy maximization and which aspects resist such treatment. It sharpens the boundary between what could be emergent and what appears irreducible. Importantly, entropic gravity does not claim that space-time is unreal or that forces are illusions. It reframes gravity as a large-scale description of underlying degrees of freedom, much like elasticity describes solids without referencing atoms directly. Elastic forces are real and measurable, even though they are emergent. Gravity could be similar. But analogy has limits. Elasticity breaks down at small scales, where atomic structure matters. Gravity, however, has been tested down to extremely small distances without deviation from geometric predictions. Any emergent account must explain why the effective description is so robust across scales. For now, entropic gravity remains an interpretation rather than a replacement. It does not negate general relativity. It depends on it. It does not deny geometry. It seeks to explain why geometry behaves the way it does. Whether that explanation is ultimately correct is unknown. What can be stated with confidence is that gravity, entropy, and information are entangled conceptually and mathematically. Attempts to separate them run into contradictions. Attempts to unify them reveal structure. Entropic gravity is one such attempt, cautious in its best form, speculative in its strongest claims. The responsible position is restraint. The idea is neither dismissed nor embraced as fact. It is examined, tested, criticized, and refined. This is how physics progresses, not by declaration, but by constraint. For most of the history of physics, space-time has been treated as the stage on which everything else happens. Objects move through space, processes unfold in time. Even when space and time were unified into space-time, they were still assumed to be fundamental. They were not explained, they were presupposed. General relativity deepened this picture by making space-time dynamic, but it did not remove its foundational role. Geometry could bend and evolve, yet it remained the basic ingredient. The question of whether space-time itself is fundamental arises only when multiple lines of evidence begin to point in the same direction. Gravity behaves geometrically. Horizons carry entropy. Information is bounded by area. Quantum correlations can reproduce geometric relationships. Each of these results stands on its own. Taken together, they invite a careful reconsideration of assumptions that were once taken for granted. In physics, emergence is not a radical idea. Many quantities once thought fundamental are now understood as effective descriptions. Temperature emerges from molecular motion. Pressure emerges from momentum exchange. Sound emerges from collective vibration. None of these concepts are illusory. They are real, measurable, and predictive, but they are not fundamental. They describe large-scale behavior without revealing microscopic structure. Space-time could belong to this same category. It could be a macroscopic description that emerges when underlying degrees of freedom are organized in a particular way. If so, geometry would not be an input to physics, but an output. Curvature would reflect collective behavior. Distance would summarize correlations. Time would parameterize change in an effective description rather than exist as a primitive backdrop. This possibility does not contradict general relativity. It reframes it. General relativity would then be analogous to fluid dynamics. It would describe how space-time behaves once it exists, not how it comes into being. Its equations would be effective laws, accurate within their domain, but silent about deeper structure. Evidence for this view does not come from speculation. It comes from breakdowns. When general relativity is pushed to extreme regimes, such as near singularities or at very small scales, it ceases to be predictive. Curvature diverges. Distances lose meaning. Time becomes ill-defined. These are not merely technical problems. They signal the limits of the theory's applicability. Quantum mechanics introduces its own limits. It forbids arbitrarily precise localization of energy and position. Attempts to probe space-time at extremely small scales require high energies that dramatically alter geometry. At some point, the act of measurement creates horizons. Space-time resists being resolved beyond a certain scale. This resistance is not imposed by technology. It is imposed by physics. These considerations suggest that space-time may not exist as a smooth continuum at all scales. The notion of a continuous manifold may be an approximation that breaks down when quantum effects dominate. Whether space-time becomes discrete, relational, or something else entirely remains unknown. What is known is that the classical picture cannot be extrapolated indefinitely. Importantly, asking whether space-time is fundamental does not mean denying its reality. Emergent phenomena are real. Temperature is real even though it emerges. A wave on the surface of the ocean is real even though it emerges from molecular motion. The question is not whether space-time exists, but at what level of description it exists. This distinction matters because it changes how problems are approached. If space-time is fundamental, then quantum gravity must quantize geometry itself. If space-time is emergent, then quantum gravity must identify the underlying degrees of freedom from which geometry arises. these are very different programs. So far, no experiment has directly probed the microscopic structure of space-time. All available evidence supports the smooth geometric description at accessible scales. This places strict constraints on any emergent model. It must reproduce general relativity with extraordinary accuracy. It must explain why space-time behaves classically over such a wide range of conditions. The emergence question therefore remains open. It is not settled by black hole entropy. It is not settled by holography. It is not settled by quantum information theory. These frameworks suggest possibilities. They do not deliver verdicts. What they do provide is discipline. They rule out certain assumptions. They reveal hidden constraints. They show that space-time, gravity, entropy, and information cannot be treated as independent concepts. Any fundamental theory must weave them together consistently. Whether space-time is fundamental or emergent is not yet known. What is known is that the question itself is now unavoidable, grounded in concrete results rather than philosophical discomfort. If space-time is emergent, then it must emerge reliably. It must emerge in the same way everywhere we look. The geometry near Earth, near the Sun, near distant galaxies, and across the observable universe obeys the same rules. General relativity works with extraordinary precision across an enormous range of scales. Any deeper description must explain this stability. Emergence cannot be fragile. It must be robust. This requirement places severe constraints on possible underlying structures. Random or loosely organized degrees of freedom would not produce a smooth, predictable geometry. The emergence of space-time would need to be governed by principles that enforce consistency, symmetry, and locality at large scales. These principles would have to suppress microscopic irregularities in the same way that fluid behavior suppresses molecular chaos. One way to understand this is through effective theories. An effective theory does not describe everything. It describes what matters at a given scale. Molecular motion matters for chemistry, but not for the flow of rivers. Atomic structure matters for solids, but not for sound waves traveling through air. In each case, the effective description is insensitive to many microscopic details. Only collective properties survive. Space-time may be similar. The smooth geometry described by general relativity could be the effective behavior of deeper degrees of freedom when viewed at large scales. Curvature would then summarize how those degrees of freedom are organized, not reveal their individual identities. This would explain why space-time appears continuous, even if it is not fundamentally so. Another clue comes from universality. Very different microscopic systems can exhibit the same macroscopic behavior. Liquids with different molecular compositions obey the same equations of fluid flow. This universality arises because the equations depend on symmetry and conservation laws, not on microscopic details. General relativity may be universal in the same way. Its equations may depend only on broad features of whatever underlies space-time, not on the specifics. This perspective also clarifies why space-time resists direct observation at very small scales. If geometry is an emergent description, then probing below its scale of validity would be like probing below the scale where temperature is meaningful. The concept itself would fail. Attempts to measure distances smaller than a certain limit would not reveal finer geometry. They would disrupt the collective behavior that gives rise to geometry in the first place. Importantly, this does not mean that space-time dissolves into randomness. Emergent structures can be extremely rigid. Crystals are emergent, yet they have precise geometry. Their regularity arises from underlying interactions that enforce order. Space-time could be similar. Its smoothness could be the result of deep organizing principles that operate below direct observation. At present, there is no experimental evidence that space-time breaks down at small scales. All tests of gravity to date are consistent with a smooth geometric description. This means that any emergent model must hide its microscopic structure extremely well. deviations from general relativity must be negligible under all tested conditions. This is a demanding requirement, and many proposed models fail to meet it. For this reason, the question of spacetime's fundamentality remains open. It is not a matter of preference. It is constrained by observation. Theoretical frameworks that suggest emergence are judged not by elegance alone, but by their ability to reproduce known physics without contradiction. What can be said with confidence is that spacetime occupies a unique position in our understanding of nature. It behaves like a physical entity. It carries energy. It can ripple. It can stretch. And yet, it may not be fundamental in the same way as the entities it governs. This tension is not a weakness. It is a guide. The question is no longer whether spacetime could be emergent in principle. The question is whether a concrete, testable framework can show how this emergence occurs while preserving everything we know to be true. Until such a framework is confirmed, spacetime remains both indispensable and mysterious. Every physical theory ultimately answers to observation. Equations may be elegant, principles may be consistent, but without contact with measurement, physics does not advance. When gravity, spacetime, and information are discussed at fundamental levels, this requirement becomes more demanding, not less. The ideas become subtle precisely because the experiments become difficult. General relativity remains one of the most thoroughly tested theories ever constructed. Its predictions are not confined to extreme environments or rare events. They appear in everyday technology and routine observation. Clocks placed at different heights tick at measurably different rates. Signals traveling near massive objects experience delays. Light bends as it passes stars and galaxies. These effects are small, but they are precise, repeatable, and unavoidable. Any proposal that alters gravity must reproduce every one of these results within experimental accuracy. The difficulty arises because the regimes where gravity is expected to reveal deeper structure lie far beyond direct reach. Quantum gravitational effects are expected to become significant at extraordinarily small distances. Attempting to probe such distances requires concentrating immense amounts of energy into tiny regions. But gravity itself prevents this. At some point, the energy density becomes large enough to form a horizon. The region becomes inaccessible. Nature enforces a limit. This limitation is not a failure of engineering, it is a physical constraint. It means that direct experiments probing the microscopic structure of spacetime may be impossible in principle. As a result, quantum gravity is tested indirectly, through consistency, through inference, and through subtle deviations from known laws. Precision experiments therefore become crucial. Instead of looking for dramatic breakdowns, physicists search for minute discrepancies. They examine how gravitational waves propagate across vast distances. They measure how clocks behave in extreme conditions. They study how the universe expanded in its earliest moments. So far, all results align with general relativity combined with quantum field theory for matter and radiation. Cosmology offers one of the few windows into extremely high-energy physics. The early universe reached temperatures and densities far beyond anything achievable today. The patterns imprinted in the cosmic microwave background carry information about those conditions. Measurements of these patterns show remarkable agreement with models based on classical spacetime geometry. No clear signature of spacetime discreteness or holographic structure has yet emerged. This absence of deviation does not falsify emergent spacetime ideas. It constrains them. Any viable framework must hide its microscopic structure extremely well. Deviations from smooth geometry must be suppressed across all tested scales. This is a demanding requirement, and it eliminates many speculative models. Holographic frameworks survive because they do not contradict known observations. They are constructed to reproduce general relativity in appropriate limits. They explain entropy bounds without modifying low-energy behavior. They remain compatible with existing data precisely because they do not introduce observable deviations where none are seen. entropic gravity proposals face a stricter test. Because they reinterpret gravity itself, they must reproduce not only static gravitational behavior, but also full relativistic dynamics. This includes gravitational waves, strong field effects, and cosmological evolution. At present, no entropic model has achieved this comprehensively. As a result, such proposals remain exploratory. Physics progresses by respecting these limits. Ideas are not rejected because they are untested. They are rejected when they contradict what is known. In the case of gravity and spacetime, the known facts impose tight boundaries. Within those boundaries, exploration continues. Outside them, speculation ends. The indirect nature of testing fundamental gravity also changes how evidence is weighed. In many areas of physics, competing theories can be separated by a single decisive experiment. In quantum gravity, separation often comes from internal consistency. A proposal must fit seamlessly with thermodynamics, quantum mechanics, and relativity all at once. If it fails in any one domain, it cannot be correct, regardless of how appealing it may appear. One of the strongest consistency requirements comes from information conservation. Quantum mechanics demands that information is preserved in time. Any theory of gravity that allows information to be destroyed outright would undermine the foundation of quantum theory. This requirement sharply constrains how horizons, evaporation, and entropy can behave. Black hole thermodynamics is not optional background material. It is a filter that eliminates entire classes of models. Another constraint comes from causality. Space-time geometry determines which events can influence which others. Signals cannot propagate faster than light. Gravitational interactions respect this structure. Any emergent description must reproduce causal behavior exactly. Small violations would accumulate over cosmic timescales and produce observable effects. None are seen. There is also the issue of locality. At everyday scales, physics is local. Objects interact with their immediate surroundings. Forces weaken with distance. Field values depend on nearby sources. If space-time is emergent from non-local information structures, that non-locality must be hidden extremely well. It must reproduce effective locality with extraordinary accuracy. This is not impossible, but it is highly restrictive. Gravitational waves provide an especially powerful test. These waves carry energy across enormous distances without dispersion beyond what general relativity predicts. Their speed matches the speed of light. Their polarization and decay match theoretical expectations. Any deviation would immediately signal new physics. So far, none has been detected. This places emergent and holographic ideas in a delicate position. They must explain why gravity behaves so cleanly as a classical field over vast scales, while still allowing for deeper structure at microscopic levels. This balance is difficult to achieve. It requires mechanisms that suppress corrections without eliminating the underlying dynamics entirely. The absence of experimental anomalies does not imply stagnation. It reflects the extraordinary success of existing theories. General relativity is not a fragile approximation waiting to collapse. It is a robust description that has survived a century of increasingly precise tests. Any successor theory must respect that success. As a result, modern research in gravity often proceeds by sharpening questions rather than proposing sweeping changes. Physicists ask which assumptions are truly necessary and which may be emergent. They ask how entropy bounds arise so universally. They ask why geometry and information appear intertwined across independent domains. These questions guide theory even when experiments lag behind. They prevent speculation from drifting too far from reality. They ensure that proposals remain accountable to known physics, even when direct testing is out of reach. Observational limits, therefore, do not weaken the scientific process. They strengthen it. They force discipline. They narrow the space of possibilities. They ensure that uncertainty is acknowledged rather than hidden. The final constraint on theories of gravity is humility. Nature does not adjust itself to human expectations. The absence of evidence is not evidence of absence, but it is a boundary that cannot be crossed lightly. When data are silent, theory must speak carefully. Many ideas about quantum gravity, holography, and emergent spacetime remain mathematically consistent, yet empirically inaccessible. This does not make them unscientific. It places them in a provisional category. They are evaluated by coherence, by their ability to unify known results, and by whether they suggest new questions that could one day be tested. But they are not promoted to conclusions. This distinction matters. History shows that physics advances when speculation is constrained, not when it is unrestrained. General relativity itself emerged not from wild imagination, but from a careful response to experimental facts about motion, light, and time. Its radical nature was imposed by evidence. The same standard applies now. There is also a risk in overstating what current ideas imply. Holography does not prove that the universe is a projection. Entropic gravity does not prove that gravity is an illusion. Quantum information approaches do not prove that spacetime is made of bits. These phrases can mislead by suggesting certainty where none exists. Precision in language reflects precision in thought. What observations currently support is limited but firm. Spacetime behaves smoothly at accessible scales. Gravity propagates at a finite speed equal to that of light. Entropy bounds hold wherever horizons appear. Information is not freely disposable. These facts constrain theory powerfully without dictating a single answer. Future progress may come from new observational windows. More sensitive gravitational wave detectors may probe stronger fields. Better cosmological data may reveal subtle imprints of early universe physics. Laboratory experiments may test gravity in regimes not yet explored. Or progress may come from theoretical breakthroughs that reveal unexpected connections between known principles. Until then, the boundary between knowledge and hypothesis must remain clear. Physics does not advance by filling gaps with certainty. It advances by mapping those gaps honestly and precisely. After tracing gravity from force to geometry, entropy from heat to information, and spacetime from background to possible emergence, the most responsible task left is not to conclude boldly, but to conclude carefully. Physics earns its strength not by certainty, but by restraint. What matters is not how far ideas can be extended, but where evidence allows them to stop. Gravity, as it stands today, is described by general relativity. This description is not provisional in the casual sense. It is one of the most thoroughly tested frameworks in all of science. Its predictions govern falling objects, orbiting planets, the bending of light, the ticking of clocks, the expansion of the universe, and the propagation of gravitational waves. Across all tested regimes, its accuracy is extraordinary. Nothing discussed in this work replaces it. Any deeper theory must reproduce it exactly wherever it has been confirmed. Entropy is equally well grounded. It is not a metaphor and not a philosophical abstraction. It is a quantity defined through counting physical possibilities. It governs irreversibility, equilibrium, and limits on transformation. Its appearance in gravitational systems is not optional or interpretive. Black holes possess entropy. Horizons possess temperature. These results arise from calculation, not analogy, and they survive every consistency check applied to them. Information, once thought abstract, is now understood to be physical. It cannot be stored without energy. It cannot be erased without cost. It cannot be compressed arbitrarily without invoking gravity. These constraints are not technological. They are fundamental. They apply to matter, radiation, and space-time alike. From these facts emerges a pattern. Entropy scales with area in gravitational systems. Information capacity is bounded by surfaces. Geometry enforces thermodynamic limits. These statements are not speculative. They are consequences of combining well-established theories. What remains uncertain is how deeply these patterns run. The holographic principle occupies a careful middle ground. It is not a proven law of nature, but neither is it an arbitrary conjecture. It is motivated by entropy bounds and realized exactly in specific theoretical settings. It demonstrates that gravity and geometry can, in principle, be encoded in lower dimensional descriptions. Beyond those settings, its status remains open. It constrains theory without dictating a final picture. Quantum information theory strengthens this picture without closing it. It shows how geometry can be reconstructed from correlations. It explains why area laws appear naturally. It demonstrates that space-time behavior can emerge from non-geometric descriptions in controlled models. But possibility is not proof. These results show that emergence is allowed, not that it is required. Entropic gravity pushes the idea further, asking whether gravity itself might be an effective consequence of entropy and information flow. As a hypothesis, it is disciplined but incomplete. It reproduces certain limits and highlights deep connections, but it has not replaced general relativity, nor has it produced decisive experimental predictions. Its value lies in what it reveals, not in what it resolves. At this point, physics stands at a boundary defined not by ignorance, but by honesty. Many connections have been uncovered. Few have been closed. What physics can honestly claim must therefore include what it cannot yet explain. Space-time may be fundamental, or it may be emergent. Both possibilities remain consistent with all current observations. There is no experiment that forces one conclusion over the other. There is no calculation that closes the question definitively. This uncertainty is not a weakness. It is a precise statement about the limits of knowledge. If space-time is fundamental, then quantum gravity must explain how geometry itself acquires quantum properties without contradiction. If space-time is emergent, then a deeper theory must explain how smooth geometry arises so reliably, so universally, and so accurately across an enormous range of scales. Both paths are difficult. Both demand new ideas that respect old results. What is clear is that gravity occupies a unique position in physics. It is not just another interaction. It defines the structure within which all interactions occur. It shapes time, distance, and causality. This makes gravity unusually resistant to unification and unusually sensitive to conceptual shifts. Any proposal that treats gravity lightly misunderstands its role. Entropy has emerged as a unifying thread, but not as an answer. It connects thermodynamics, information, and horizons. It explains why certain limits exist and why geometry behaves thermodynamically in specific contexts. But entropy does not yet explain why space-time exists or why gravity takes the form it does. It constrains explanation rather than providing it. Holography and quantum information approaches show that geometry can be reconstructed from non-geometric data in specific models. They reveal that area laws are natural rather than accidental. They show that information and geometry cannot be separated cleanly. But they stop short of demonstrating that our universe is governed by these principles in a literal sense. This distinction matters. Physics does not advance by confusing mathematical possibility with physical reality. Many consistent models can be written down. Only a few describe nature. The task is not to choose the most elegant picture, but to identify the one that survives every constraint imposed by observation. What remains certain is the direction of inquiry. Gravity cannot be understood in isolation from entropy and information. Space-time cannot be treated as an inert backdrop disconnected from physical limits. Horizons, bounds, and correlations are not side effects. They are signals. Future progress will likely come from unexpected connections rather than direct measurement. It may come from new ways of combining existing principles rather than introducing entirely new ones. Or it may come from observations that reveal subtle deviations where none were expected. Until then, the discipline of physics requires patience. Certainty will not be declared prematurely. Questions will remain open because nature has not yet answered them. That is not failure. It is the normal state of science at a frontier. The most honest conclusion physics can offer is not a declaration, but a boundary. Within that boundary, much has been learned. Beyond it, much remains unresolved. Gravity is known to be geometric in its behavior. Entropy is known to impose real and unavoidable limits. Information is known to be physical and constrained. Horizons are known to behave thermodynamically. These are not interpretations. They are results. What remains unknown is whether these results point toward a single deeper explanation or whether they reflect several independent principles meeting at a shared boundary. It is tempting to compress them into one narrative, to say that space-time is nothing but information, or that gravity is nothing but entropy. Such statements feel satisfying, but they move faster than evidence allows. Physics does not reward speed, it rewards precision. The history of science offers a useful reminder. Newton described gravity without knowing what gravity was. Einstein described space-time curvature without knowing what space-time was made of. Each framework deepened understanding while leaving foundational questions open. Progress did not require final answers, it required correct ones within known limits. The current situation is similar. The connection between gravity, entropy, and information is real, but its ultimate meaning is not settled. The holographic principle shows that geometry can be encoded differently. Quantum information theory shows that correlations can reproduce spatial relationships. Entropic reasoning shows that forces can emerge from statistics. None of these results alone or together forces a single conclusion. What they do force is discipline. Any future theory must explain why general relativity works so well. It must explain why entropy scales with area in gravitational systems. It must preserve information in a quantum sense. It must respect causality and locality where they have been tested. These are not optional constraints. They are non-negotiable. Uncertainty, in this context, is not ignorance. It is resolution without closure. The questions are sharper now than they were a century ago. They are defined mathematically. They are constrained by data. They are no longer philosophical curiosities. They are technical problems waiting for solutions that nature will accept. Whether space-time is fundamental or emergent, whether gravity is geometric at all scales or only effectively so, whether entropy plays a constitutive role or merely a constraining one, these questions remain open because the universe has not yet revealed its full structure. Physics has not failed to answer them. It has earned the right to ask them precisely. The safest conclusion is also the strongest. Physics can say what gravity does. It can say how entropy behaves. It can say where information is limited. It cannot yet say why space-time exists in the form it does. That honesty is not a retreat. It is the foundation on which future understanding will be built.